Good afternoon. First of all, I would like to thank Professor Patnaik and his team members for this excellent teamwork for organizing such a big conference and inviting me to deliver a talk in this conference. So, actually, if you see this, this title of this talk is general talk. So, in the introduction part, I would like to discuss on this only, and then I will discuss our recent results on this topic. So, let me start. This is for the non-experts. So, these very simple things. So, there is an object where positive and negative charges are separated. So, it forms an electric dipole. Okay. So, now we can say it's a polar order. So, now if you can change this order by any means, for example, by applying electric fields in the opposite direction, so then there is a reversal of polarization, then we can say this is a ferroelectric materials. Okay. So, and there is one more property is that in these cases space inversion symmetry is broken. So, I will give you with the simple example. So, let us consider these numbers 1 to 6 in this way, and now if you apply this inversion operator, as you know the inversion operator is operated only on a point. So, if you operate on the origin, so basically the number will exchange. So, basically x, y, z will be minus x minus y minus z, and in this way if the object becomes same, so it is centrosymmetric, but if it is not, then it is non-centrosymmetric, and that is, or we can say that space inversion symmetry is broken. So, one of the best example is the barium titanate. Sujit Das already discussed a lot. However, I would like to say that the simple things in the paraelectric state, here titanium is sitting at the center of the regular octahedra. I say regular, and octahedral corners are occupied by oxygens, and these are the barium ones. So, if you apply the inversion symmetry operator, so it should be symmetric. So, it is centrosymmetric structure. However, below the ferroelectric ordering, so because of this off centering of the titanium atom, so space inversion symmetry is broken. So, thus ferroelectricity emerges. So, now next question will come that how, so ferroelectricity emerges because of static charge distribution, but magnetism appears because of the dynamics of charge. So, because of the electrons, as you know that, so electron can have the either spin motion or the orbital motion, which gives rise to the magnetism. So, let us consider this is anticlockwise rotation of a spin, and that gives us the magnetic moment direction in the upward direction. So, now if we apply the time reversal operator on I becomes minus I. What is I? I is the E by T. So, now T becomes minus T, so that is why I becomes minus I. So, that means the current rotation will be in the opposite direction, clockwise direction, and the moment will be opposite. So, in this way, so the time reversal symmetry is broken. So, another example, so suppose this is your ferromagnetic materials have spins pointed along up direction, and if you apply this operator, so it will be down. So, for any magnetic ordering, the time reversal symmetry is broken. So, now so if we find both coexist, ferroelectricity and magnetism, magnetic order, so those materials are called that multiferroic materials, and those are very rare materials where space inversion symmetry and time reversal symmetry are broken. So, I will talk on this subject. So, in these cases, in these multiferroics, the ferroelectricity meets with the magnetism. So, there are two types of multiferroics, one is type 1 and type 2. Type 1, the best celebrated example of type 1 multiferroics is that bismuth ferrite, where origin of ferroelectricity is because of the bismuth 3 plus, whereas iron 3 plus provides the magnetism. So, the relation between these two is very weak, because origin of ferroelectricity and magnetism basically it creates the antiferromagnetic order are different. So, the coupling between these two is very weak. But this can be solved for the type 2 multiferroics. These are the classical examples where the long range magnetic order itself can break the space inversion symmetry, and thus ferroelectricity emerges. So in these cases, the coupling between these two is very strong. But the problem is that the magnetoelectric coupling for type 2 multiferroics is much stronger than type 1, but it has been observed at very low temperature. That is the problem with this. So what is the focus on this? The focus is that, so large magnetoelectric coupling we can find, but close to the room temperature. So but it should be for the type 2 multiferroics, because the coupling we should have stronger coupling. So let me realize how this coupling issue can come from the Greensburg-Landau theory. So this is the free energy expression, and this consists of P is the polarization, E is the electric field, M is the magnetic polarization or magnetization, H is the magnetic field. So now we see this term P. So if you have a derivative with respect to E, that gives us the P. Okay. So if you can have P, and the right hand side, if you see this consisting of E, H both. So P is a function of E and H. On the other hand, look at this expression. If you have the derivative with respect to H, so that gives you the M, and that includes the H and E, magnetic and electric field. So magnetoelectric coupling is possible. So experimentally what we do that, suppose for ferroelectrics, what we do that, we can tune the polarization by changing electric field. For the magnetic material, we can tune the magnetization by using magnetic field. Now if you can tune the polarization by applying magnetic field and magnetization by electric field, then it is possible only if you have the magnetoelectric coupling. So this has a lot of technological applications, so that is why people are working on this, because you can read magnetically or write electrically, that is possible. So now I will show our results on these rare earth ferrites. That also provides a new high temperature type 2 multiferroics, and I will discuss the result based on these publications. So before that, I should discuss why I have chosen the rare earth ferrites. So this is the first example of multiferroic order in dysprosium ferrite. So for dysprosium ferrite, at high temperature, there is an antiferromagnetic ordering at 645 Kelvin, and that happens because of the iron spin only. And at low temperature, because of the rare earth ordering, so there is another magnetic ordering at 4 Kelvin, and the ferroelectricity observed below this temperature. So at very low temperature, but the magnetoelectric coupling was found very high, and because of the first report, so it appeared in PRL. So next year there was another report for gadolinium ferrite, where the ferroelectricity appeared below the gadolinium ordering temperature, but it appeared in Nature Materials because they first observed that the coupling can be explained from the composite domain wall motion. So that is why it appeared in Nature Material. So after 3 years, there was another report, so that is on samarium ferrite, and the authors claim that, so in that cases that iron moment ordering was 670, and they claim that they also observed the ferroelectric order at that temperature, and they pointed out that there is a spin counting which leads to the ferroelectricity, and that was really was a remarkable breakthrough. But unfortunately, after 2 years there was another report on this same material, where they proposed that it is not a canted antiferromagnetic structure, it is a K equal to 0 magnetic structure, that means parallel antiferromagnetic magnetic structure, and they told that there is no ferroelectricity. That also appeared in PRL, and that instinct us to work on this rare earth ferrite to search the high temperature ferroelectric order whether it is possible. So we have taken terbium ferrite, it lies in between dysprosium and gadolinium, and holmium ferrite, which is just next to the dysprosium in the periodic table. So let me start with the background of the magnetic properties, which is already published. So because of the iron, so because of the iron moment ordering, so for holmium and terbium it orders at 647 and 650 Kelvin, and these are the magnetic states they explained from the neutron results. With lowering of temperature, however, this magnetic state is K equal to 0 collinear magnetic structure. And with lowering of temperature, because of the interaction hybridization between the rare earth and iron, there is another spin reorientation temperature lies in between 48 to 50, 48 to 58 depending on the reports, different reports for holmium, and 8.5 for the terbium compound. And finally, at low temperature, there is another ordering, that is because of the rare earth. The important point is that below the rare earth ordering temperature, the magnetic state is exactly same like what they observed in the high temperature, below the high temperature magnetic ordering. So we studied in crystals. I am not going into the crystal preparation. However, we orient the crystal. So at room temperature, this has a PBNM phase. So so that is orthorhombic. So we cut along A axis, B axis, and C axis for our measurement. So let me start with the heat capacity and dielectric permittivity, because if there are any ferroelectric ordering, that is indicated first in the dielectric permittivity. So we recorded the dielectric permittivity as a function of temperature for holmium compound, and it does not show any indication, any anomaly. However, when we made the measurement on the heat capacity, so if you see these highlights, there is a slope change around this temperature, and at low temperature there is also another peak that corresponds to the spin reorientation transition temperature, which is not of our interest. Similar measurement was performed for terbium, but it shows the peak in the real part of the dielectric permittivity at around close to 200 Kelvin, and also we extended our measurement at low temperature. So at the rare earth ordering temperature, there is also another peak we observed that indicates there is a ferroelectric order for terbium 1. However, we observed the ferroelectricity even for the holmium compound around 210 Kelvin. So here you see, just consider the results for H equal to 0 and just ignore the results, the curve with non-zero magnetic field. I will come back to this again. The important point is that when we reverse the Pauling field, there was a reversal of the polarization. That proves it is a ferroelectric ordering around 210 Kelvin. And that was further confirmed from this PE loop measurement. At 300 Kelvin, it is a paraelectric like. At 200 Kelvin, just below this ordering, so there is a loop, and at 10 Kelvin also there is a well defined loop. Actually, I forgot to say that all the measurements, in all the measurements we observe this ferroelectricity only in the C direction. In the A and B direction we did not observe. Why? I will come back at the end of this talk. So the similar measurement was done for the terbium ferrite. Also we observed the high temperature ferroelectric order, and we also observed the low temperature ferroelectric order below this terbium ordering temperature, where the magnetization shows also a peak, well defined peak. So we have two ferroelectric ordering for the terbium compound. So far the report we had, the established one is that all the report was that ferroelectricity can appear below the rare earth ordering temperature, which we observed here. But in addition, we observed that even at high temperature, quite high temperature, there is a ferroelectric order. So of course, we also performed the similar measurement, that P loop measurements, that also confirms the ferroelectric order. And yeah, so we did not observe any polarization along A and B axis. So let me show you so far the important results, where we can see the type 2 multiferroic shows the ordering close to the room temperature. The first report was appeared in copper oxide. So the magnetic ordering was 230, and in between 230 to 213 there was ferroelectric order, but the polarization value was quite low. And samarium ferrite is the controversial one, so I should not tell anything about this. And for chromium oxide it shows the magnetic order at 307 Kelvin, but it is not a natural ferroelectric order. So at 0, if you apply magnetic field H equal to 0, there is no ferroelectric ordering, but if you apply magnetic field, ferroelectric order starts. So at 9 Tesla, so there is a ferroelectric order and the value is still low value is observed for chromium oxide, and these are our results. So it shows the magnetic order at very high temperature, these two, and ferroelectric order close to 200 Kelvin, and even the ferroelectric polarization value is quite high. The next question will come, why this ferroelectric order appears. So in order to address this issue, we perform the synchrotron diffraction at P09 Petra 3 beamline, and you see this 11L scan with temperature. So there is a shift in positions. So see, this is the position as a function of temperature. It shows a anomaly. Maybe it's around, maybe you can say it's a peak close to the ferroelectric ordering temperature. And just inverse of this provides you the C lattice constant scaled by lattice constant at 300 Kelvin, and this also shows the minima here, and that's also reflected in the intensity plot also. There is an indication. But in the terbium ferrite, there is no such strong indication. However, if you can believe that there is a small change in some solder, so it becomes asymmetric, and if you plot the lattice constant, there is no anomaly. However, at low temperature, at the spin reorientation temperature and the terbium ordering temperature, there is a strong indication indicating the strong magnetoelastic coupling, but there is no elastic coupling at the high temperature ferroelectric order. So this does not answer the origin. So to address this issue, we perform the neutron diffraction. So it was done in ILL D19. So actually we started calculating the displacement, because this has a collinear magnetic structure. It cannot explain directly the origin of ferroelectricity. So only the atomic displacement can explain it, but with the PBNM high temperature structure we could not explain it. So we considered the isotropy subgroup, the polar PBN21 structure, and this is the magnetic structure. These arrows are green arrows are the ordering of the iron moment, exactly antiparallel, and these are collinear structure. And if you see, these are the displacement is shown here in this figure. So the purple one shows the displacement of iron, but within the unit cell, if you calculate it, it cancel out. Similarly, this is the holnium. This green one is for the holnium, small displacement. This also cancels out within the unit cell. And oxygen 2, so below this, so we are proposing structural transitions from PBNM to PNA21 at the ferroelectric ordering, and at that time there are 3 oxygens, oxygen 1, oxygen 2 and oxygen 3. But oxygen 2 and oxygen 3 does not show any displacement. However, the oxygen O1, oxygen 1 shows the displacement along C axis, and it does not cancels out within the unit cell, and that is why we observe the ferroelectricity along the C direction only. Similarly, these are the displacement for calculated from the refinement of the neutron diffraction at 200 Kelvin, and see, these are the here in this case oxygen 1, for this case is oxygen 2 shows the displacement, non-zero displacement along C axis, and if you calculate, this is not the 3-dimensional picture, but if you calculate along A and B, this will cancel out, only non-zero value will be along the C direction, and that can explain the ferroelectric order along C direction. So we also calculated magnetoelectric coupling. We recorded the polarization as a function of temperature at different magnetic field, and we plotted here. So this plot is the change in polarization due to magnetic field scaled by the polarization at 0 magnetic field, and this is the percentage of change, and it increases and it becomes maximum close to 4 Tesla, and then it decreases for polonium compound, and the value is quite high, it's at 20%. Similar measurement was performed for terbium compound, both at high temperature ferroelectric order and low temperature ferroelectric order. The results was contrast, so it decreases considerably and becomes changes was maximum around 3 Tesla, and for 2 Kelvin it was also shows the change was maximum close to 2 Tesla. However, the results was just opposite. However, the changes at this case is close to 37%. And how it happens? So to address this issue, we also performed the magnetostriction experiment at P09 beamline. So what we did that we recorded the diffraction peak as a function of magnetic field. So with increasing magnetic field, it increases and then it shows the decrease. On the other hand, here it decreases and it becomes it's non-monotonous. So the take home message from here is that when the delta P decreases, so delta C increases. When delta P increases, delta C decreases. That means when there is a contraction along C axis, the change in polarization due to magnetic field increases. We also performed the dynamic magnetoelectric coupling. What is that? So we just swept the magnetic field between plus minus 10 kilohertz state. So this red curve up and down with time, and we recorded the pyroelectric current which provides the polarization, and this also oscillates between the 2 points, but it doesn't matches with the same phases. The periodic time is different. However, at low temperature the results was different. So when we changes the field, there was no change almost. Only it shows the changes when the magnetic field crossed the 0 value. So just above and below. So just above and after there is a signal, and that is systematic. So these are the dynamic results of the magnetoelectric coupling. So now coming to the conclusions. So we observe the high temperature ferroelectric order for both the compounds, and magnetoelectric coupling is up to 20% for holmium compound, and for 8% at 180 Kelvin and 40% at low temperature. So the magnetoelectric coupling for terbium was attributed to the magnetostriction, and these results also partly solved the controversy on the possible high temperature multiferroic order in rare earth ferrite, because samarium one is controversial one, but we could partially solve that problem that at high temperature ferroelectric order is possible in rare earth ferrites. So with this I would like to acknowledge the students, those who are involved with this work, and Oscar Favelo, who did the neutron experiment, and Stemfer. He was in Petra 3 but now is in Argonne National Laboratory. He performed this synchrotron diffraction experiment. And I would like to acknowledge Tapun Chatterjee. He is no more, but he was the mastermind to explain the ferroelectricity why we observed here. So for all the neutron diffraction experiment management was done, initiated by him. So I would like to acknowledge the projects, and this is my current group of students. Thank you very much for your kind attention.